In a commercial building setting with multiple tenants and a single utility service drop, the requirement for a fuse disconnect on a 600 amp disconnect feeding multiple meters is a critical aspect of electrical safety and code compliance. The National Electrical Code, or NEC, provides specific guidelines on overcurrent protection and disconnect requirements to ensure the safe operation of electrical systems. This narration will delve into the details of whether the 600 amp disconnect in a described scenario is required to be fused, referencing relevant sections of the 2008 NEC. Firstly, it is important to understand the purpose of overcurrent protection. Overcurrent protection devices, such as fuses or circuit breakers, are designed to protect electrical equipment and wiring from excessive current that could cause overheating, damage, or even fire. These devices are intended to interrupt the flow of current when it exceeds a predetermined level, thereby preventing potentially hazardous situations. Secondly, the NEC mandates overcurrent protection for conductors at their ampacity rating. Ampacity refers to the current carrying capacity of a conductor, which is determined by factors such as the conductor's size, material, insulation type, and installation conditions. The overcurrent protection device must be sized to protect the conductor against overloads and short circuits, but it should not be so small that it causes nuisance tripping under normal operating conditions. Thirdly, in the context of a service disconnect, the NEC requires that each service conductor have overcurrent protection. A service disconnect is the main point of disconnection between the utility's service conductors and the building's electrical system. It is typically the first point of isolation for the building's electrical system and is used to de-energize the entire system for maintenance or emergency purposes. Fourthly, according to the NEC, service conductors are required to have overcurrent protection at the point where they receive their supply. This protection must be sized no greater than the ampacity of the service conductors. The overcurrent protection can be provided by a fuse or a circuit breaker. Fifthly, when multiple disconnects are used in a service arrangement, the NEC provides specific rules for sizing and coordination. In a multi-tenant building with a single service drop, it is common to have a main service disconnect that feeds multiple meters, each serving an individual tenant. In this scenario, the main service disconnect must have overcurrent protection sized appropriately for the service conductors. Sixthly, the individual tenant meters and disconnects also require overcurrent protection. The overcurrent protection for these devices must be sized no greater than the ampacity of the conductors feeding the individual tenant loads. This ensures that each tenant's electrical system is protected against overcurrent conditions. Seventhly, the 600 amp disconnect in the described scenario is likely required to be fused. Given that it is a main service disconnect feeding multiple meters, it must have overcurrent protection sized no greater than the ampacity of the service conductors. The specific fuse size will depend on the size and ampacity of the service conductors, as well as any applicable directing factors. Eighthly, the installation of the 600 amp disconnect and associated overcurrent protection must comply with all applicable NEC requirements. This includes proper sizing of conductors, selection of appropriate overcurrent protection devices, and proper installation and grounding of all equipment. It is important to consult the NEC and any local electrical codes to ensure compliance with all applicable regulations. Ninthly, in the provided scenario, the fact that the equipment is grouped on the exterior of the building does not change the requirement for overcurrent protection. The NEC applies regardless of the location of the equipment. The location may, however, influence the type of enclosure and protection required for the equipment, such as weatherproofing or resistance to environmental factors. Tenthly, the wireways used to connect the 600 amp disconnect to the meters must also be properly sized and installed. Wireways are metal or non-metallic troughs used to enclose and protect conductors. The NEC provides specific requirements for the fill capacity of wireways, as well as the types of conductors that can be installed in them. 11thly, the wireway must be sized to accommodate the number and size of conductors installed in it. The NEC specifies the maximum fill percentage for wireways, which is typically 40% of the cross-sectional area of the wireway. This ensures that the conductors are not overcrowded, which could lead to overheating and insulation damage. 12thly, the conductors installed in the wireway must be properly insulated and rated for the voltage and current they will be carrying. The NEC provides tables that specify the ampacity of different types of conductors based on their size, insulation type, and installation conditions. 13thly, the connections between the conductors and the meters must be made using approved connectors and terminals. The connectors must be sized appropriately for the conductors and must be properly tightened to ensure secure connection. Loose connections can cause overheating and arcing, which can be a fire hazard. 14thly, grounding is an essential aspect of electrical safety. All electrical equipment, including the 600 amp disconnect, meters, and wireways, must be properly grounded. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and clear the fault. 15thly, the grounding system must comply with all applicable NEC requirements. This includes the use of appropriate grounding electrodes, grounding conductors, and bonding techniques. The grounding system must be designed to minimize the risk of electric shock and to protect equipment from damage. 16thly, it is important to note that the NEC is updated regularly, and the requirements may change over time. It is essential to consult the latest edition of the NEC and any local electrical codes to ensure compliance with all applicable regulations. 17thly, in summary, the 600 amp disconnect in the described scenario is likely required to be fused. The specific fuse size will depend on the size and ampacity of the service conductors, as well as any applicable derating factors. The installation must comply with all applicable NEC requirements, including proper sizing of conductors, selection of appropriate overcurrent protection devices, and proper grounding of all equipment. 18thly, the use of a fused disconnect provides an additional layer of protection against overcurrent conditions. Fuses are reliable and relatively inexpensive overcurrent protection devices that can help to prevent damage to equipment and wiring, as well as reduce the risk of fire and electric shock. 19thly, the decision to use a fused disconnect versus a circuit breaker disconnect is often based on factors such as cost, availability, and personal preference. Both types of disconnects can provide adequate overcurrent protection if properly sized and installed. However, fuses offer certain advantages, such as their ability to interrupt very high fault currents and their inherent current limiting capabilities. 20thly, when selecting a fuse for the 600 amp disconnect, it is important to choose a fuse that is specifically designed for service entrance applications. These fuses are typically rated for high voltages and currents and are designed to withstand the stresses of service entrance conditions. 21stly, the fuse should also have an interrupting rating that is sufficient to handle the available fault current at the service entrance. The interrupting rating is the maximum amount of current that the fuse can safely interrupt without failing. 22ndly, the 2008 NEC provides detailed information on the selection and installation of overcurrent protection devices, including fuses and circuit breakers. It is essential to consult the NEC to ensure that the selected overcurrent protection device meets all applicable requirements. 23rdly, the NEC also provides guidance on the coordination of overcurrent protection devices. Coordination refers to the selection and arrangement of overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the extent of the outage. 24thly, proper coordination of overcurrent protection devices is essential for maintaining the reliability and availability of the electrical system. It helps to prevent unnecessary outages and to protect equipment from damage. 25thly, in the context of the multi-tenant building, it is important to coordinate the overcurrent protection devices at the main service disconnect with the overcurrent protection devices at the individual tenant meters. This will help to ensure that a fault in one tenant's electrical system will not cause an outage for the entire building. 26thly, in addition to the NEC, local electrical codes may also have specific requirements for overcurrent protection and disconnects. It is important to consult with the local electrical inspector to ensure compliance with all applicable regulations. 27thly, the electrical inspector can provide guidance on the interpretation of the NEC and local codes and can help to ensure that the installation is safe and compliant. 28thly, It is also important to have a qualified electrician perform the installation of the 600 amp disconnect and associated overcurrent protection. A qualified electrician will have the knowledge and experience necessary to ensure that the installation is done correctly and safely. 29thly, the electrician should be familiar with the NEC and local codes and should be able to properly size and install the overcurrent protection devices. The electrician should also be able to perform the necessary testing and inspections to ensure that the installation is working properly. 30thly, regular maintenance and inspection of the electrical system are also important for ensuring its continued safety and reliability. The overcurrent protection devices should be inspected periodically to ensure that they are in good working condition. 31stly, the connection should be checked for tightness, and the conductors should be inspected for damage. Any problems that are found should be corrected promptly. 32ndly, in conclusion, the 600 amp disconnect in the described scenario is likely required to be fused based on the need for overcurrent protection for service conductors as mandated by the NEC. Compliance with the NEC and local electrical codes is essential for ensuring the safe and reliable operation of the electrical system. Proper sizing of conductors, selection of appropriate overcurrent protection devices, proper grounding of all equipment, and regular maintenance and inspection are all critical aspects of electrical safety. 33rdly, it is important to remember that electrical work can be dangerous, and it should only be performed by qualified individuals. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work for you. 34thly, by following the guidelines and requirements of the NEC and local electrical codes, you can help to ensure the safety of your electrical system and protect yourself and others from the hazards of electricity. The specifics of NEC 230.95 regarding ground fault protection should also be reviewed and considered. 35thly, NEC 230.95 addresses ground fault protection of equipment. This section generally requires ground fault protection for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 600 volts phase to phase for each service disconnect rated 1000 amps or more. The purpose is to provide protection of equipment from damaging line to ground fault currents. 36thly, if the 600 amp disconnect in the scenario is serving as a service disconnect and is rated at 1000 amps or more and the voltage is within the range specified, ground fault protection would be required in addition to the overcurrent protection previously discussed. Ground fault protection operates to trip the service disconnect at a predetermined ground fault current level. 37thly, it is important to understand the difference between overcurrent protection and ground fault protection. Overcurrent protection is designed to protect against overloads and short circuits, while ground fault protection is designed to protect against ground faults. Overcurrent protection devices typically trip at much higher current levels than ground fault protection devices. 38thly, ground fault protection is typically provided by a ground fault circuit interrupter, or GFCI. A GFCI is a device that monitors the current flowing in the circuit and detects any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI trips the circuit, interrupting the flow of current. 39thly, GFCIs are commonly used in residential and commercial applications to protect against electric shock. They are typically installed in bathrooms, kitchens, and other areas where there is a risk of water exposure. 40thly, ground fault protection of equipment is not intended to protect people from electric shock. It is designed to protect equipment from damage caused by ground faults. GFCIs are used to protect people from electric shock. 41stly, in the context of the multi-tenant building, ground fault protection may be required at the main service disconnect if the disconnect is rated at 1000 amps or more and the voltage is within the range specified. The ground fault protection would operate to trip the service disconnect if a ground fault occurs in the building's electrical system. 42ndly, the installation of ground fault protection must comply with all applicable NEC requirements. This includes proper sizing of the ground fault protection device, proper installation and grounding of all equipment, and proper testing of the ground fault protection system. 43rdly, it is important to consult the NEC and any local electrical codes to determine whether ground fault protection is required for the 600 amp disconnect in the described scenario. The NEC provides detailed information on the requirements for ground fault protection of equipment. 44thly, in addition to the NEC requirements, there may also be local requirements for ground fault protection. It is important to check with the local electrical inspector to ensure compliance with all applicable regulations. 45thly, the electrical inspector can provide guidance on the interpretation of the NEC and local codes and can help to ensure that the installation is safe and compliant. 46thly, it is also important to have a qualified electrician perform the installation of the ground fault protection system. A qualified electrician will have the knowledge and experience necessary to ensure that the installation is done correctly and safely. 47thly, the electrician should be familiar with the NEC and local codes and should be able to properly size and install the ground fault protection device. The electrician should also be able to perform the necessary testing and inspections to ensure that the ground fault protection system is working properly. 48thly, regular maintenance and inspection of the ground fault protection system are also important for ensuring its continued safety and reliability. The ground fault protection device should be tested periodically to ensure that it is tripping properly. 49thly, the connections should be checked for tightness and the conductors should be inspected for damage. Any problems that are found should be corrected promptly. 50thly, the specifics of the 2008 NEC requirements can be found in Article 230.95. It is important to consult this article to ensure compliance with all applicable regulations regarding ground fault protection of equipment.